thanks a lot for the invitation. It's really been a good week. So much fun. I will talk about the joint work, quite in progress still. If I were a very cautious person, I would maybe put an asterisk next to a theorem or something like this, but I'm not. So state the theorems as they are. And if you are a cautious person, you can insert an asterisk in your head. Louis is from Geneva, somehow very appropriate that this is the venue where I talk about it for the first time. So we already heard about top-weight cohomology of MGN in several talks. Francis Brown. Okay, but so let me begin by saying something about what the handlebody group is. So by BG, genus G handlebody. Everyone knows what a handlebody is. It looks like this, but it's solid, it's filled, it's a three-manifold boundary. And I'm going to write sigma G for its boundary, which is an oriented surface of G. And the handlebody group, which appears in the title, is pi 0 diff of BG. And I'm going to denote this group by HG. And if I have a diffeomorphism of the handlebody, I can restrict it to the boundary. As to pi 0 diff sigma G, and I'm going to use that gamma G, the usual mapping class group of the surface. And this map is in fact injective, so the handlebody group is a subgroup of the mapping class group of the surface. I also want versions of this with marked points and marked disks on the boundary. I'm going to write marked points with a subscript. And I hope this is clear. Look at diffeomorphism fixing either a finite set of points or a finite set of disks lying on the surface. And these groups, HGN and gamma GN, they're similar in many ways. And I want to make a table to sort of bring out some of the similarities, focusing on the properties. But maybe the first thing I want to say is I think DG is actually also HG, meaning that all of the connected components of this topological group are contractible. You can Hatcher. And the exact same thing is true in the surface case, where it's due to Teichmüller. The virtual homological dimension of both of these groups is known. The BCD of HG is 4G minus 5, which is due to Hirosen. And the BCD of gamma G is also 4G minus 5, which is due to Harrow. there is homological G1 error. So in a range increasing with the genus, the homology stabilizes. This is true here. Where it's due to Hatcher and Ball. Stable cohomology is known rationally. Here, stable cohomology. And everything is rational in this talk. I will omit the Q coefficients. I'll just write this and I mean Q coefficients. It's a polynomial ring on certain classes, the kappa classes. This is a consequence of a stronger topological theorem that identifies a limiting homotopy type of this after plus construction with a certain infinite loop space. Need to add some advice. And on this side, stable cohomology is also polynomial ring. It's generated by kappa 2, kappa 4. So the inclusion of the handlebody group into the mapping class group gives you map on stable cohomology, and that map kills the odd kappas and preserves the even kappas. This is also the cohomology of an infinite loop space. And this is due to Hatcher, but announced it and never published a proof. And then Steiner, Brunner, who also has a different proof, but it's not on the archive. And now, yeah, maybe there's room for one more entry at the bottom here. The order one is greater than 1 G due to Harrer and Tallier. We heard about this in Michael Borinsky's talk. The Euler characteristic is asymptotically proportional to the actual Euler characteristic. This is the orbifold Euler characteristic. And the actual Euler characteristic is the alternating sum of better numbers. This gives you a bound on the asymptotics, and you see that it grows very, very fast, and it alternates in sign. So we know that there's vastly more a priori than what is accounted for by the stable classes. Here we have no idea what the Euler characteristic is. And in particular, as far as I know, it could very well have been the case that most cohomology was accounted for by everything stable here. But the results I will tell you about today show that it's not the case. So that's a rapid introduction to the handlebody group. I also want to say something about top-weight cohomology, even though we've already heard about it. So what makes the smooth compact variety in complex numbers? E inside of X is a strict normal crossing divisor. So I have a collection of hypersurfaces, smooth, and they intersect transversely at the point. And in this situation, it's a very explicit description due to the lean of how to construct a mixed word structure. the cohomology of x minus b. This next Hodge structure comes with a weight filtration, and if you isolate only the top weight part of this mixed Hodge structure, so the part that has the largest possible weight it can have, the description becomes almost purely combinatorial. What I mean by that is that in general, this description due to the linear involves, the cohomologies of all of these divisors, all of the components of these divisors and all of their intersections. But if I only care about the top weight part, I only see H0. So I see a copy of Q for each component. That's why it's all combinatorics. And this goes back to the 70s. Now in the particular case that X is MGN bar, to be and the boundary of the open moduli space MGN. And that's a normal cosmic divisor. It's not strict, but close enough. And this purely combinatorial description of the top weight part, in this case, it very naturally is a graph complex. Top weight cohomology of MGN is given by a graph complex. So what are the graphs? So the graphs have a genus decoration at vertices. Genus 0 vertices are at least trivalent. And we're contacting a tadpole. Raises the genus. And there are signs involved as always. And take the set of edges and you give it a sign where you have an automorphism that swaps two edges. That's a that minus sign. The differential is edge contraction. So that's the graph complex that just falls out of the general picture. Now the diagram. Triangulations and pain. It's not how they state it, but somehow this is the key thing that they prove that makes everything work, is that this graph complex is quite isomorphic quotient complex where all whenever you have a graph that has a vertex with a genus bigger than 0, you set that to 0 in the complex. Let's decomment this. Why is this important? Well, this quotient complex where we plot these hierarchy values, this is considered
hairs.
Hairs, yeah.
We forget about hairs.
No. Hairy graph. This quotient complex is the graph complex. So the upshot, and that's maybe the appropriate way to state the theorem, is that homology, or let's say homology of the graph complex is identified in the top-weight homology MGM.
No, not the concept complex, it's a head one.
Yeah, okay. So
HGC, HGC.
if I do
I
this,
see.
it's actually one of those conceivage. If I insert the hairs, the theorem is still true, and then I have to put an in here and an in here, and I have to do sum of all the hairs. Maybe I just do. And this is important for several reasons. And one of them is at some point I would prefer to dualize, and maybe I'll do that now. The H0 of the graph complex injects into H0 of GC is isomorphic to Thomas ERT1, which contains Francis really around figures. So the enormous amount of cohomology of the statement MD from this construction. And I didn't state any signs here. If you work out exactly what the signs are, you see that the cohomology ends up in degree 4g minus 6. So exactly one below the virtual cohomological dimension. So it's very far away from the unstable range, and it grows much quicker than any previously known construction of cohomology classes. And in particular, it falsified the conjecture said that cohomology close to the zero to infinity with G. I also want to discuss a geometric interpretation of this map from the graph complex to probably this is the point where I want to dualize. So instead of thinking about top weight cohomology, I will take bottom weight cohomology with compact support. Poincaré dual. In many ways, this is more natural. There is a geometric interpretation like this. It turns out that there's a map of MGM to a space called MGM trop, and we heard about in Francis' talk, and it's a tropicalization morphism. I call it TR, and it's continuous proper map logical stacks. If you don't like stacks, think of topological spaces. I have to tell you what this space MGM trop is. MGM trop is a space of metric graphs. Instead of defining it carefully, I will give an example of what a cell looks like. It's a cell complex. Suppose I have a graph of precisely the type that appeared here. So I might have parallel edges. I might have a tadpole. I might have some legs. So this a metric on this would be the assignment of a length to each edge here. So once I've assigned lengths to all of these edges, that gives me a point in the moduli space, and it's a moduli space of tropical curves of genus 1 plus 2 plus the first Belly number of this graph, which is 2, so that's 5. The number of legs, which is 4, M5,4. And the cell that corresponds to this combinatorial graph looks like it's positive real numbers, 5 copies of it, corresponding to these edges. But it's actually an orbicell complex. I said it's a stack, not a space. So I take the quotient automorphisms of the graph. So here I have 2 automorphisms, one that swaps these 2 parallel edges, and another automorphism that reverses the direction of this edge. But that automorphism does nothing on R5 plus. But this one, it swaps these 2 factors. And I take the stack quotient. So I have these open cells indexed by graphs, and I glue them together along edge contractions. So if I contract some edge here, and let the edge length go to 0, I get a cell of dimension 1 less, and it's glued to the boundary of this orthant. Okay. So the combinatorics of this cell complex is looked up. So it exactly models the combinatorics of this graph complex. And if I compute the compact support cohomology of this space, I can compute that using cellular chains, and then I have a copy of Q for each cell. And I get exactly on the nose this graph complex as the cellular chains with compact support of this MGM. Not quite, sorry. If I take cellular chains with compact support, this is too well. The differential is edge expansion instead of edge contraction. So that's a space MGM trop. It's glued together by cells this way. And now I can define the tropicalization map. I want to interpret this space MGM as the space of hyperbolic metrics on the genus G surface. And I want to have n cusps for this hyperbolic metric. Now I want to choose some positive real number epsilon. Small enough that closed geodesics on such a surface of length less than epsilon are always disjoint. Epsilon depends on G and M, but it does not depend on the particular hyperbolic metric. There is a single epsilon that works for all hyperbolic metrics. So let me draw a picture that illustrates how the tropicalization works then. So I have my surface, and I have a hyperbolic metric on it. This gives me a point of MGN. Now I ask, what are the short geodesics? What are the geodesics on the surface that are shorter than epsilon? Let's say that they look like this. I have one here, and here. So these are the short geodesics. And they have some lengths that I call A1, A2.
Sorry, yeah, a bit confused, but epsilon is big enough so as you still have them, right? Maybe epsilon is too small and
Yeah, this could be an empty set.
okay.
Yeah, that's fine.
Okay.
Yeah. But no matter what epsilon is,
Yeah.
you will always have some hyperbolic metrics
Oh.
where there are short geodesics,
Okay.
arbitrary
Mhm.
small lengths.
Mhm.
For sure, this could be the empty set. Absolutely.
No, because you're drawing many of them, and that's why I get confused.
Yeah. But if I do this, it would not be a very good example. But I should do that one. Now what you do, you take these short geodesics and you crush each of them to a point. And then you get a nodal surface. I don't have to draw that nodal surface, but I can draw the dual graph that indexes it. So in this business of stable curves, we index nodal curves by their dual graph, where we have a vertex for each component. When I collapse these, we have two irreducible components, one here and one here. And then I have an edge in the graph for each node, indexing which components are connected by the node. So here I have one node that goes between these two. Here I have another node. Here I have a node which goes from this component itself. And then I have a decoration at each vertex, giving the genus of the normalized component. This is a genus 1 component. And this is a genus 0 component, because there are no actual holes when I resolve this node. And I want to assign lengths to these. I do that by the formula that Li is minus the logarithm of AI divided by S. That's in R. And if I had no short geodesics at all, here a single vertex. no limits. And then the point is that cohomology of the graph complex is cohomology of the complex support by this. Sorry, I'm getting ahead of myself.
So maybe I first the definition is right, but I'm again a little bit confused. Typically, why do you want those tropical parameters to be positive? We usually tropical parameters, right? They take values from whatever or is either plus or minus infinity in the joint. So I mean, kind of why this? What's the reason for this restriction? Right, we want those geodesics to be short enough for those logs to be positive, but I mean, it's strange for
I want to end up in this space.
Yeah, okay. Now, of course, it's a definition, so.
So sphere with 3 graphs will give us theta.
Sorry?
Sphere with 3 cusps will give us theta graph. Okay, right.
Theta.
Theta graph.
Yeah.
No, there's one component. No, a flower or something.
Let's talk about it later.
Oh, yeah, I don't know. A point.
So this is the first ingredient. I have this space MGM trough and this tropicalization map. But I also have an open subspace that Francis talked about in his talk. And I don't know what the standard name for it is. I would call it YGM. It's open. Well, and this is the latest of grade 0 that confers. All of these vertices are
Hairs here as well, right?
Yeah, and this example, it's
No hair, but yeah, then it's clear. It will be one vertex with 3 hairs.
What is this space YGN? It's actually quite familiar to, I think, several people here. It's outer space modulo this group GGSM, which is the homotopy automorphisms. The graph like this. This is endpoints here. The G0 is of FG and G1 is and for M bigger, these are generalizations of these groups, and this is one studied by Color and Boatman. This general family of groups has been studied by Cohen, Thatcher, Hasselblad, and Boatman. This is open because the complement, if you contract something to get the genus vertex, you always get something of smaller dimension. And support of this YGM. This is naturally computed by Harry graph complex. Homology is functorial for open inclusions. This map realizes illusion thing. Well, this community diagram. YGN here, which sits as an open subspace. Tropicalization map from MDM. And taking compact support cohomology of everything inside, you get Kontsevich's graph complex here with hairs, mapping to this other graph complex, and then from the linear, compact support cohomology is contravariant for proper maps. So compact support cohomology of this guy maps into compact support cohomology of that guy. It's injective and it embeds as the weight zero part. I'm taking cohomology with compact support. Yes.
Is it obvious that the map induced by the topicalization map lands in weight zero? There's no mixed hot structure.
Not this description, really. That's
What's the argument?
Sorry?
Can I ask you what the argument is?
Yeah, it's not clear from this abstract description that it's compatible with what the linear did. But now, if you look at this diagram, you see that there's another way to factor this. Suppose I define UGN as ER inverse YGN. And that's open from GN. Naturally has a proper map down here. So I can take compact cohomology, put it back here, and then map into here. And this diagram commutes. And what is this space UGM? That's maybe not so clear, but it turns out that this is actually a very nice space. And that's the point in the talk. UGM is the classifying space in the handlebody group. So corollary is that GRT1 is going to inject into here because GRT1 is in here and it survives this, so it's going to survive into here as well. This is then the same as homology in degree 6G minus 6. Maybe I don't want to put N here since I wrote GRT1. Star. And again, this is in the BCD, since the handlebody group and the mapping class group are the same BCD. So I get an enormous amount of cohomology, and it's very, very unstable. There are many natural questions, I think, motivated by this. One is, can we say something about the Euler characteristic of the handle-body group? Could be interesting to see how much of the cohomology we can account for. Does there have to be lots more of it? There's kind of a graph that calculates it, that comes out of this perspective. I don't know if that's interesting fact about the cohomology of the mapping class group is that it always vanishes rationally in the virtual cohomological dimension. You can ask if the same is true for HG. Great. So the main ingredient in proving this is a theorem of Gian-Siracusa. I want to talk about that theorem briefly in 10 minutes. Consider the following modular opera of handle bodies. In genus G and area to N, in the satisfying place of the handle body groups, genus G with N marked disks. If I have marked disks, I can glue handle bodies together. And in genus 0, there is no difference between the handle body group and the mapping class group. There's kind of a canonical way to fill a genus 0 handle body, whereas there is, a genus 0 surface can be canonically filled to a handle body. Not the case. So genus 0, which 0n is the same as gamma 0m, and when I take this genus 0 part of this, I get the genus 0 surface operad, which is the frame little disks. Consider as a cyclic operad. And here, one is that modular operad modular envelope. Derive the envelope of frame little disks and you get the handle body. And when you hear this, you say, wow, that sounds reasonable. If you imagine I have genus 0 Lego pieces, like bolts. Like, I'm mixing metaphors. Imagine they're not at all Legos. But you stick these, whatever. You stick them together, you get handle bodies, and you can build every handle body in this way. There's nothing intuitive about this claim. But I have to say, what is the derived modular envelope of a cyclic orthogram? Let O be a cyclic modular orthogram. This derived modular envelope, and what is it? In genus G and area to N, I'm going to do the following. I'm going to look at of genus G with N legs. In the padpole here, and to such a graph, I would attach four And then any way of contracting edges in this diagram is going to give me, such as if I contract that top edge. This thing, and if I look at all graphs of all the decorations, I get a diagram in spaces, and I can take the whole limit of that. And this is and if I take in the actual co-limit, I would get the non-derived model. And here's then the idea. I'm going to look at its surface opera. Modular opera. Into 0 is the gradient of disks. So I get a canonical map from the modular envelope of the 0 part of this to this opera. Now I'm going to represent this space in terms of hyperbolic geometry. I look at the moduli space of hyperbolic surfaces with geodesic boundaries. And to be precise, I want to consider that as a colored opera, where the space of colors is the interval from 0 to epsilon. And these are the allowed lengths of these boundary components. That means that only short boundaries are allowed. And when I take the derived modular envelope, I get an explicit map like this. And I can think about what is the image of that derived modular envelope map. Well, then I get genus 0, the genus G hyperbolic surfaces with a very special property that they can be built out of hyperbolic surfaces in such a way that when I glue them together from these genus 0 pieces, I only use short geodesics. That means that the image of this derived modular envelope map is this collection of open subspaces, UG, that I just defined. But of the fibers, if I pick a map point to this UG, and I think about what the fiber looks like, it's the geometric realization of the collection of cut systems that I can cut along to build it using short geodesics. But that category has an initial object because there's a maximal cut system given by all short geodesics on that hyperbola. And that's the proof. And I skipped over some parts. In particular, one important detail is here I have surfaces with boundary components and actually wanted cusps. And when I glue together handle bodies, I have to forget the circle action because I can rotate at the same time. Both are taken care of in the same way, and you have to think about the effect of the genus 0. Not at least morally correct. Okay, my time is up. Thank you for listening.
Are there questions? Dan?
Completely, does that mean that Feynman transform of BB computes the cohomology of EH T upper M?
Not quite. And I think it's big, yeah. Because of this. And Siracusa works with which have this genus 0 arity 2 component, which is explicitly disallowed by Getter and Capranov. What I think is correct is that if you take M0 and bar, hypercommutative operad, extend by 0 to higher genera and take the Feynman transform of that, that computes the handlebody. And the reason is that including the components has the effect of killing the circle action in the Feynman transform, because it's like a Borel construction at each edge, because I can insert arbitrarily many copies of this. But killing the circle action in framed little disks, it gives you the hypercommutative.
Right, let's then done again.